now we're done with talking about hurricanes, and we're going to transition just for a few minutes onto a few other types of extreme weather. Now, I should stress that what we're going to be talking about now is a little bit more of a gray area. Hurricanes, tornadoes, thunderstorms, they've been well researched. We really understand their behavior. We're able to categorize them. We're able to classify them, track them, give them names, and do all kinds of things to allow them to be warned or to allow people to be warned of them. But what we're going to be talking about in the next few slides is relatively new meteorology. It's stuff that we're still kind of understanding, and it's not as well defined, especially when we talk about superstorms. And then I'm going to end the lecture by talking about just a few other extreme types of weather, and there's many more I could talk about, but we'd be here for several hours, and I know you guys don't want to do that. I don't want to do that, so let's jump in. So first off, what is a superstorm? Well, a superstorm is caused by some kind of major imbalance. We've already talked about the fact that weather is caused by imbalances. However, most of the time those imbalances are very small and they're spread out over a large area. However, there are some times when you have a warm tropical air mass and it's colliding with a cold Arctic air mass, and you have the hottest of the hot and the coldest of the cold colliding together. And that can create tremendous pressure gradients, tremendous temperature gradients, tremendous amounts of rain and wind, and tremendous storm systems. You also can have instances where hurricanes will collide into mid-latitude cyclones. And each one of these can create a storm that is very intense and oftentimes much more unprecedented than your normal mid-latitude cyclone. And so we call these superstorms. So why do superstorms happen? Well, superstorms happen because of those extremes. Examples of this were the 1991 perfect storm, where Hurricane Grace, an intense category 2, 3, 4, I think eventually 5 storm, an intense storm slammed into an Arctic cold front that was moving down from the polar regions. And when you had these two that were colliding together, you had a very large difference in temperature over a very small area. Lots of energy can form in that. Superstorm Sandy was a very similar case. And in fact, a lot of people had even said before Sandy formed, they said, man, this looks just like the perfect storm. The only difference is that the perfect storm was primarily an ocean storm, whereas Superstorm Sandy actually hit land. Another good example of this was the storm of the century, which formed in 1993, and this formed when the polar jet stream and the subtropical jet stream collided over the east coast of the United States. There's a good documentary on this. In fact, there's good documentaries on all of these, and I'll post a few in the description below. So there's a few really good documentaries on these. So here's Hurricane Sandy. This was the predecessor of Superstorm Sandy. Now, the way hurricanes typically work, and we had talked about this last time, or 2 lectures ago actually, is usually there's this big subtropical high out here in the Atlantic, and out here we call this the Bermuda High. And this high pressure system would normally take a storm like Sandy and it would hurl it harmlessly out to sea. However, in this case, that high pressure was not there. Not only was the high pressure not there, but there was an intense jet stream that had formed, and just due to the right conditions, a very odd pattern developed in it. And this odd pattern allowed Sandy to travel up the East Coast and actually turn inland. And so that's actually what happened with Sandy. Now, before Sandy actually underwent any of this, though, it had started out as just a normal Category 3 major hurricane. It hit Cuba, moved through there quickly. They picked up and cleaned up their damage. There was definitely some damage and some deaths due to it there. But then it began to travel up the eastern seaboard. And without that Bermuda High present, and with this odd jet stream present, Sandy just fed right into it. In addition to this, let's see if I can draw this pretty well here. In addition to this, there was a cold front approaching the region. Like this. And Sandy actually interacted with this cold front. And the two storm systems fed off of each other. So that's also what led to this growth. Here is Hurricane Sandy as it was undergoing that transition from hurricane to superstorm. Here's that cold front beginning to dissipate. The hurricane is actually now wrapping around this whole frontal system. A warm front has actually now developed on one end of the hurricane. This hurricane is essentially merging with this mid-latitude cyclone here. See where the cursor went? Right there. The hurricane is essentially merging with this mid-latitude cyclone. That's just one example. Another example, and this is one I'm actually going to have you watch a documentary on, and again, it's in the description below, the 1993 Storm of the Century. Now, the 1993 Storm of the Century actually started on a warm springtime day in the Gulf of Mexico. And what happened was the polar jet stream to the north was beginning to sag south. The subtropical jet stream in the south was sagging north, and a Gulf low developed from this subtropical jet stream. It then moved and fed into this area where the two jet streams were colliding. And this created a tremendous mid-latitude cyclone and a very deep low-pressure system with very cold air behind it, very warm air in front of it. And as a result, there was this tremendous storm that developed along this entire frontal boundary. Here in the south, a squall line developed that created high winds, heavy rain, lots of lightning, and several damaging tornadoes. And it also had such low pressure that it also created storm surge. The northern half of this storm system actually experienced extreme blizzard conditions. And when I say northern half, I mean pretty much everything north of Florida. This whole area here was extreme blizzard conditions. This storm caused over 100 deaths, billions of dollars of damage, and it was a turning point in forecasting. So, how did this storm form? It formed because extremely cold air clashed with extremely warm, moist air. That warm, moist air fed into the cyclone, allowing it to intensify, creating severe blizzard conditions in the northern part of the storm, and a squall line in the southern part of the storm. Somewhat similar to Sandy, one other thing I'm going to mention about both of these storms is they formed during the transition seasons. Now, when I say transition seasons, I'm talking about spring and fall. Because in spring, you're transitioning from the cold of winter to the warmth of summer. In the spring, you're transitioning from the cold of winter to the warmth of summer. In the fall, you're going the other way. You're transitioning from the warmth of summer to the cold of winter. And during these seasons, you can get air masses that are clashing with each other. The seasons, in a sense, are battling it out. And those battles can be pretty epic. And so many of these superstorms actually form during the spring and fall months. The last superstorm I'll talk about, also a fall-time storm, was the 1991 perfect storm. This one, very similar to Sandy, formed from a strong polar cold front colliding with Hurricane Grace in October of 1991. This created a very intense low-pressure system that actually eventually became a hurricane. However, the storm stayed off the coast. And so, really, coastal areas and shipping got the worst of it. Most areas inland did not experience tremendous damage from it. However, ships were greatly affected, and the big famous example of this was the Andrea Gale. There's a whole movie called The Perfect Storm about this ship that was having bad luck all catching season, decided to go way out into the ocean, caught a lot of fish, and tried to muscle it through this storm. And unfortunately, they were lost in it. This is the perfect storm at its most intense moment. And as you can see, luckily it was primarily off the coast. Now, that's it for superstorms. The last thing I'm going to talk about in this module is other types of extreme weather. So there are other extreme weather events, and this is just a sampling of other extreme weather events. Heat waves, droughts, ice storms, fire weather, and so on. Now, how do heat waves form? Well, first off, what is a heat wave? Well, I'm sure we all know and love them here in California. A heat wave is simply a prolonged period of above average air temperature. What actually causes a heat wave, though? Well, it all goes back to the jet stream. The jet stream actually gives us a lot of information about warm air and cold air. Whenever the jet stream is further north, there's a warm air mass to the south. Whenever the jet stream is further to the south, there's a big cold air mass. Now, heat waves are actually very typical, and in fact, even as I'm writing this lecture, we're actually going through a heat wave right now. And not that big of a deal. The only people that are really going to be affected by this are people that are very sensitive to weather conditions, people that are in poor health, the elderly, young children. But anybody who is in really good health might be uncomfortable, but for the most part, they're going to be okay. So most heat waves are typical. However, some heat waves can actually be exceptionally long and exceptionally intense. And when I say intense, what I mean is that temperatures can be 20, 30, 40 degrees Fahrenheit above average. And if you live in a location that just isn't used to that kind of heat, you're in trouble. A good example of this was in 2003. Most of Europe in the summer months of 2003 experienced an extreme heat wave. And most of the regions that experience this extreme heat wave are usually expecting and are really used to cooler weather. Their homes, their infrastructure isn't built to protect them from the heat. It's built to protect them from the cold. As a result, when it is hot, their homes can heat up really bad, their infrastructure can fail, and things can get really nasty really quick. In 2003, over 30,000 people died in France alone, just in 2003 from extreme heat. Now, all of these heat waves are caused by a ridge in the jet stream, and this ridge produces an upper level high pressure system, and it creates what's called a heat dome. And this heat dome spans over many states, or many countries, depending on where you're at, and it can stay in place for several days. So, as I just mentioned, the 2003 European heat wave was an example of this. And usually when these heat waves happen, as I just mentioned, they're usually very widespread. It's not just a small area, just one state that's necessarily getting it. It could be many states or many countries even. What about droughts? Well, droughts are definitely a much more gray area than heat waves. And the reason why is because droughts have numerous things that can cause them. Our drought that we experienced here in California was caused by an abnormal ridge of high pressure. This ridge of high pressure took any storms that would have developed, that would have hit California, and it pushed them north up and over the Pacific coastline, up into Alaska and British Columbia, and then back down into the eastern end of the United States. And this produced a drought. However, you can live in a location that's receiving normal rainfall. And if your community relies on a river that comes from somewhere else, if that somewhere else is experiencing a drought, you're now in a drought. And so there are many things that can cause droughts. Increased water use, increased population, not being careful about your water use can lead to drought conditions. Simply, a drought is just a period where we just don't have enough water. Now, droughts are very long term. They're not extreme weather events in that we're not going to have a drought that lasts a week. Droughts usually last for years, months or years. A very prolonged period of abnormally low precipitation and abnormally low water supply. A few other extreme weather events that I'm going to talk about, and these are ones I think I've already talked about, but I'm just going to talk about them again. Ice storms. Ice storms occur when you have lots of what's called freezing rain. And freezing rain, if you recall from Module 4, freezing rain forms when you have snow that melts in a warm layer and then enters this inversion where it freezes again. And in the case of freezing rain, the water can't freeze quickly enough and it freezes as it hits the ground. Now, this can make things look very beautiful. This image here looks very beautiful, especially seeing it as a Californian who doesn't have to experience this. However, this water can stick itself to trees. Water is very heavy. It can cause limbs on those trees to break. If it's on power lines, it can cause those power lines to snap, and people can be without power. It can cause any kind of flimsy structure to break down. Freezing rain also makes driving hazardous because essentially you're driving on a skating rink. What ice storms need to form is they need an inversion, and usually a very shallow inversion, meaning that the cold air is only maybe a few hundred feet above the surface of the earth. And it's just close enough to the ground where the rain can't melt or freeze in time before it hits the ground. It needs to freeze on contact. Warm fronts are a good way that these can form. The last thing I'm going to talk about, everything else we've talked about is stuff that we don't experience here in California. But one thing I do want to talk about is fire weather. And I am not an expert on this. If you want to learn more about fire weather, we actually have a top fire weather research lab just down the street at San Jose State University. I'd love to put you in touch with the people there. But fire weather occurs whenever conditions are ripe for fires. There are three things that need to be present for conditions to be ripe for fires. You need to have hot, dry, windy air. The air needs to be hot because it brings the vegetation near the ground much closer to the burning point. So not as much heat is needed to burn it. You need dry air because dry air is void of moisture. If you don't have any moisture, that makes it harder for these flames to be put out. So a tiny spark can form and it can quickly erupt into a blaze. And then finally, high winds. High winds do two things. One, they fan the flame in that they feed oxygen into the flame. The other thing that they do, though, is they also allow the flame to spread. So not only is the flame getting stronger, it's also spreading. And so when we have these conditions in place, fire weather ends up becoming a big concern. Now, when that happens, we actually have a special weather product that we issue. It's called a red flag warning. And meteorologists will issue a red flag warning whenever the conditions are ripe for fire formation, whenever fires can easily happen. So usually when it's hot, dry, and windy, that's when we get these red flag warnings. And here in Northern California, in the fall time when we experience what are called Diablo winds, that's a key example of red flag type weather. If you're in Southern California, or if you know anybody in Southern California, they get what's called the Santa Ana winds. Those also produce red flag warning type weather. So to review of extreme weather in general, and really everything I showed you is just a taste of extreme weather. There's so much more to it. But extreme weather involves some kind of abnormal condition, some kind of other than average weather conditions, some kind of event that can pose a danger to lives and property. And a few examples of extreme weather that we talked about: severe thunderstorms, tornadoes, hurricanes, blizzards, heat waves, superstorms, droughts, fire weather. But again, this is just the tip of the iceberg. There's so many different types of extreme weather. Now, one question that I'm sure a lot of you are probably asking yourself, and a question I get a lot, is this stuff caused by climate change? Well, we're going to talk about that in the next module. So until then, I'm Terrence Mullins. Thank you for watching.